This is Jeff Anderson, who will tell us about, being sure about simulations or confident.
Okay, and let's see, I want to get back to the start here. So, yeah, the only reason for doing this live, there's 20 versions of this talk sitting out there on the web. And so the only reason for doing this is so that the people who are here live can interrupt and ask questions. So do that. In particular, about terminology, if you have a specific application you want to mention as we're going through this, so I can be thinking about how to apply my ideas to that, anything like that. And I'll stop off and on and ask for questions too. But really, the only reason for doing this is to make it interactive. So let's do that. So I'm going to talk about building forecast systems with a tool called the Ensemble Kalman filter. And I come out of atmospheric numerical weather prediction, but at this point, the tools that we build are really extremely general. The science that we do is really for anything where you can make a prediction with some sort of mathematical model. And I will use initially an example from just everyday life, and then I'll use some weather examples later on because most people have experienced weather, and so it's a good place to start. But as I said, if you have specific applications and partway through the talk you say, is this really relevant to what I'm doing? If you'll just mention your application to me, maybe that can help. So I'm located here at the National Center for Atmospheric Research. I'm part of the Data Assimilation Research section here. NCAR is an awfully nice place to visit. So here's the view I had coming in on my end of my commute up the hill to our location this morning. It's not currently snowing. It snowed a little bit earlier. It's going to snow later. But we're right here on the edge of the mountains. We are the gateway to Boulder's extensive system of mountain parks and hiking trails. And so if you visit us, you can go out the back door and hike too. I know there's a lot of Google locations that are nice too, but anyway, the reason for us to do this is we're always looking for collaborators who have interesting challenges for our tools that we could work together with to try and find solutions that would work for them while we learn about ways that might make our current tools less efficient or break. We want to make them more general. So, as I said, I'm going to start with a really simple case. If we were all together in the same room, and there's a few variants of this talk online where you can see this, I actually have this nice red racquetball I'm holding in my hands, and I use that to get the audience's attention by throwing it at them. So it's always a nice benefit to be able to throw stuff at your audience. The reason for doing that is I'm now going to talk about a really idealized simulation of the act of catching a ball that is thrown at you by a person. And so the figure up there right now is the idealized problem we're going to solve. So that is hypothetically me there on the left of the figure holding this red ball. And we're going to assume that I threw it in an arc that looks like this. So I released the ball, and after 2 seconds, it reached a height that was convenient for whoever I threw it at, maybe Greg sitting at home in his kitchen, to reach out his hands and have them positioned under the ball. And so the prediction, the forecast system we want to build here is a system that will let us predict where the ball is going to be at a certain time so that we can get our hands underneath it and catch it. So in order to do that forecasting, we need a couple of things. The obvious thing is we need what I'm going to refer to as a prediction model. And again, as I mentioned, one of the challenges of giving this talk to a diverse audience is that there are different terminologies that have arisen for exactly the same thing across different fields. And sometimes there's conflicting terminologies where the same word is used for different things in different fields. I will try to make it clear what I'm talking about, but if you have confusion about a term, it's important that you interrupt me and say, hey, Jeff, what do you really mean by a prediction model? I don't quite get it. So in this particular case, with this ball flying through, in the idealized case here, it's just flying through a two-dimensional space. So we just have two variables, x and y. And as I go through the talk, I'm going to use the term state variables, which is something that evolved in dynamical systems and geosciences. A state variable, in this case, the x position or horizontal position of the ball, and the y position, the vertical position of the ball. The state variables are the things that give us the information about what's going on in the system now and allow us to use a prediction model, that's the two equations here, to say what's going to be going on in that system in the future. So in this simple ball example, the ball is going to continue moving with a uniform velocity. So that's the first equation here in the horizontal direction. It's going to be acted on by gravity in the vertical direction. So we have the additional gravitational acceleration term. And of course, this is just high school physics here. So very, very basic stuff. Excuse me. I'm still coming back from last week's flu here. So hopefully I'll keep my voice throughout. So one of the problems here, however, is a prediction model is not enough to help us catch the ball if we are uncertain about where the ball is right now. So when I threw that ball at you, you might not have been paying attention. And so the initial positions, x initial and y initial, when I released the ball from my hand, and the initial velocities of the ball, the u is the horizontal velocity and the v is the vertical velocity in the equations up here. So those things might be not accurately known. And so for now, I'm going to assume in this illustrative problem that all we really know is something about the probability distribution of me and the way that I throw. And so you have an approximate estimate by looking at me of how tall I am when I'm standing in front of the room and how long my arms are, where my shoulders positioned, maybe the speed of my arm as I'm swinging to throw this ball at you, and the angle of my arm at the time I release it. But again, there's a lot of uncertainty in these things. You can probably put a probability distribution on my height. So Anderson's probably between 5 feet 6 inches and 6 feet 6 inches tall. And you can probably put an estimate on the release angle. Well, it was somewhere between 30 and 50 degrees from the vertical. And the speed of the arm was probably between 1.5 and 2.5 meters per second. But all of these things have uncertainty related to them. And so if I go back to now this sample problem, I'm going to proceed to solve problems of prediction using what is referred to as an ensemble method in geosciences, and in particular in atmospheric sciences. It is related to Monte Carlo methods, which have a broad usage, although what I'm going to develop for you is technically not exactly a Monte Carlo method. It sure looks like one. And again, there's other names for this type of approach in different application fields. In the example I have now, we're going to assume that you have these uncertainties about me, the thrower of the ball. And so you could do a lot of different simulation cases where you have different estimates of my height, of my arm length, of the release position of the ball. And the initial position here, just for this example, there's 50 balls here shown by the blue dots, and the red dot shows the actual truth. Because this is a simulation, an observing system simulation experiment is the formal name for this in many fields. Because it's a simulation, I'm going to know the truth in red, and I'm going to try to use a method to reproduce, to learn as much about that red as possible. And these 50 random samples from the thrower here, I can show what happens if I plug those into the model, the parabolic motion, and that's what I get. And so if I run through it again, you can see that, well, it's not completely unknown where the ball is going to go, but there's a huge amount of uncertainty just trying to guess how I threw the ball at you. So the red ball's here after 2 seconds. Some of the balls are way up here, far away from where you might try to catch it. Some of them have bounced once. I think there's one on here that's even bounced twice. Some of them have flown far over your head, so you weren't going to catch those. So there's this huge amount of uncertainty at the initial time about where we're going to catch it. I'm going to just stop for a minute and make sure that everyone's still hearing me. So if you'll just someone respond.
Yep.
All good.
Very good. And if there are any questions, go ahead and interrupt. When we get a little bit further, and I'll definitely pause for some questions intentionally too. So I have a prediction model, which I had on the previous slide back. The other thing I need now is something that's referred to as an observing system. It takes observations. The term measurement is used in some fields of science. Basically, I need some sort of instrument. In the original case, that was the eyes of the person who caught the ball. But here for this idealized experiment, perhaps a photo measurer, a radar gun, something that can take an estimate of the position of the ball at a particular time. And of course, it's always important to remember that for a variety of reasons, going right down to the uncertainty principle, observations or measurements have errors associated with them. So I'm going to get these measurements that are have some added error, or noisy is another term for that. And in this simulation, I'm going to assume that I could observe the ball independently about every half second. So since this is a 2-second trajectory, that means I'm going to get a total of 4 observations up to the time I catch it. So here's the truth trajectory shown again in red, and here's the true position at half a second. And as I said, the observation I have is going to be an observation of the position there, and it's shown by the red plus here. And obviously, it's not at exactly the position the ball really was, because I am simulating here an instrument that has some error. And that error distribution, which I'm specifying for the instrument, if it were a real instrument, the person who built it, the engineers who built it, would give us an estimate of those errors. And so I'm showing the simulated error distribution here as equal probability contours on what is actually a normal probability distribution here. The details of that aren't really important for the hypothetical example for now. But the bottom line is the observation says the ball was here after half a second, and there's uncertainty associated with that. And so how I'm going to proceed now is I'm going to combine the information from observations at different times. So there's the second one at 1 second, another one at 1.5 seconds, and the final one at 2 seconds when the ball has reached its point where it's going to be caught. So what I'm going to do now is what is called data assimilation in geosciences, and in particular in numerical weather prediction, where this field was first brought to its mature form. It goes by many, many other names in different fields: data fusion, state estimation, filtering, other things. And so again, if you're wondering if a term you've heard or a term you use is the same thing, interrupt and ask that. So data assimilation combines forecasts from some previous time with observations. It statistically combines these things in a quasi-optimal method, and it produces a new estimate of the state variables of the system, in this case, the position of the ball. In weather, it's called an analysis. It can be called a posterior by statisticians, sometimes called a subsequent initial condition. But basically, this is an improved estimate combining information from earlier forecasts and observations of the position of the ball. And so I'll illustrate this again in a minute. But basically, the simplest way to proceed to do this is the following. Again, I can take a large number of guesses of how the ball was moving when it was released, and I can forecast them forward with the prediction model to the time at which I take my first observation. And because I have this uncertainty associated with the observation, depending upon how close my forecast position in one of the blue ones is to that red observation, I can say that ones that are closer to the observation are going to be more likely. And in fact, I can quantify that relative likelihood. And I've done that here. I'm showing 50 relatively likely guesses of the first position of the ball. And the ones that are closer to the observation, it's a little bit hard here to see in the black cross. The ones that are closer to the observations are given a darker blue color, which is consistent with them being more likely. And the ones that are further away are given a lighter blue color, which means they're less likely. And there's even less likely ones, which I didn't include on the plot here, which would have lighter and lighter blue colors. So I've illustrated this with 50 here. And in one sense, I could define this idea of an analysis or an ensemble analysis is these 50 estimates of where the ball is and their associated likelihood, their associated relative probability. And so now with data assimilation, what I want to do is basically come up with an iterative or sequential procedure to improve my prediction as I get further and further, closer and closer to the time that I'm going to try to catch the ball. So data assimilation systems of this type, they're often called sequential. Sequential forecast systems is one term for them. And so I'm going to combine my forecasts out to a half second with the observations at a half second with this data assimilation. And I'm then going to use those for initial conditions to make a forecast out to the time of the next observation, or further in this case. So illustrating this, I've shown in dashed lines here the prediction from these likely analysis ensemble members at ½ second out to 2 seconds. And you can see there's still quite a bit of uncertainty in where the ball is going to be. However, the most likely ones are generally closer to where the ball ends up. And there's definitely less uncertainty here than there was when I hadn't used the first observation. You remember that first simulation showing the blue trajectories, they were all over the place. Some of them were up here, some of them had bounced a number of times, some of them had flown way out here. And so we've started to reduce our uncertainty for the forecast at time 2. And so we can keep repeating this procedure. We can now use the observations at time 1. And so I take my forecast that were started from time 0.5, and I now adjust their likelihood by basically multiplying in the likelihood that they are close to the second observation. And so now trajectories of the ball that are close, possible trajectories that are close to both observations, are more likely than ones that are really close to one observation or the other. And so now I've used the first 2 observations, and here is my new ensemble analysis. You can see that the uncertainty is that how spread out they are is getting smaller, and I can make forecasts now from time 1.0 seconds out to time 2.0 seconds. And again, you can see that the uncertainty at 2 seconds is continuing to reduce. I failed to mention on the last slide, the 50 estimates that are out here are color-coded. Darker blue means more likely. But the probability weighted average, which we call an ensemble mean in geoscience, is shown in green. That is the most likely place that we are predicting the ball will arrive after 2 seconds. Okay, so it's not exactly where the ball is really going to be, but it's in the vicinity. And so we can keep cycling this procedure, so we can use the observations now at 1.5 seconds. You can see that there is less and less what we would call spread or dispersion in these 50 likely trajectories here. And then I can make a forecast now. This is a 1/2 second lead forecast. So this is right before I have to try to catch the ball. And you can see now that, again, there's much less uncertainty. And this best estimate, the ensemble mean in green, is actually very close in this case to the position where the ball ends up. So if we had a robot now that was simulating this catch and was trying to catch the ball, by using its estimates of what the throw was like and the observations from these 3 times, it could be pretty close to guessing where it would need to position itself to catch the ball at 2 seconds. Okay, so I'm going to do a quick summary here of this again. So these are just slides I already showed, but basically the process here is, as we move from our initial estimates of the trajectory of the ball and use observations at subsequent times, we start reducing the uncertainty. So this is a 1.5 second forecast, a 1 second forecast, and a ½ second forecast. And so we reduce the uncertainty, and in general, although this is a probabilistic result, as we reduce the uncertainty, the ensemble mean, our best estimate, gets closer to the place the ball actually goes. We could get unlucky and have just really bad observations that just the instrument sort of at random didn't work very well. And so sometimes it's possible that things actually get worse for the ensemble mean as time goes by. But something that doesn't happen is our estimate of the uncertainty doesn't go up, it goes down. I'm going to stop here for a minute and ask if there's any questions about this really basic example I've given, or where I'm trying to go with this. Okay.
I've got a question here actually about some terms I've heard before, like particle filters,
okay,
where at each time point you resample the particles. That's not happening here though, right?
That's correct. And what I'm going to do, I'll postpone that question, the answer for that, for around 15 slides here. I'll actually talk a little bit about particle filters then. You already know the answer because you're right. There is a resampling phase in classical particle filters that you aren't seeing here.
Okay, yeah.
Other questions? Okay, I'll keep moving forward then, and again, interrupt at any time. There's a number of other things one can get from this process. given the brevity of the talk today, I will not show examples of all of them. I'll show one more example, and then I'll give a list. These methods of doing a forecast system like this are extremely powerful in their most general forms, as illustrated here. One thing you can get is what's called a reanalysis, sometimes called a smoother estimate in statistics. The basic idea here is, instead of being interested in where the ball is going to be after 2 seconds, I want to know as accurately as possible where the ball was after 1/2 second. And in this particular case, I'm not limiting myself to knowing that in advance. I'm actually willing to use the observations in the future also to help me refine this estimate of where the ball was. And so if you focus on the estimate at 1/2 time, all these blue trajectories passing near the red ball here, as I use subsequent observations at 1 second, 1.5 seconds, I actually don't have the 2-second one here, but you can see as I use the subsequent observations, the estimate of where the ball was at 1/2 second gets better. So it is possible to use information from the future and information from the past at any time along a sequence of forecast trajectories to improve your knowledge of where the ball actually was. So this is just the big long list in a much longer tutorial framework. And by the way, we have a large variety of tutorial material online. I'll give you pointers to that at the end. All of these things are mentioned in those materials. There's lots and lots of things I said you can do with these. So we've talked about making analyses, so that's initial conditions, and forecasts of state variables. I just talked about smoothing estimates or doing a reanalysis. One can estimate model parameters. In this particular idealized example, let's suppose that for some odd reason we didn't know what planet we had just landed on or what the gravitational constant little g was on that planet. One could use the observations to actually estimate the value of g in that case. Now, that's obviously sort of an absurd example, but there are many, many models that we're trying to make predictions with where there are things which I'm referring to as parameters. The equations don't tell us how they change in time, but they are important inputs to the equations that we may not know accurately. And data assimilation methods like this can be used to get better estimates of those. We can get estimates of the initial conditions. So in this idealized example, where was my arm when the ball was released? How long is my arm? We can get estimates of errors in the model itself. This particular simple example doesn't have really good things, but let's suppose that for some crazy reason, we just put a factor of 1.1 in the horizontal equation so that the model was accelerating the horizontal velocity of the ball. We could detect that type of error, a systematic acceleration of the ball, by looking at the observations and then try to correct that. We could do the same thing for the observing system. So if this instrument we were using was somehow miscalibrated so that it was always reporting the ball's position, let's say at the incorrect time, 1/10 of a second too early, we could actually use these procedures to identify that error in the observing system and correct for it. Similarly, we can use it to design observing systems. We could ask the question, well, hypothetically, suppose I could buy an instrument that would observe the velocity of the ball. Okay, I could buy myself a radar gun. I could simulate, in this case, what the effect of using such an instrument would be. Would it improve my forecasts? Would it improve them by a lot? Would it be worth it for the money? So those types of experiments can be done in idealized settings like this, but also in real cases. External forcing. Let's suppose that we were really doing this in a very windy room so that the ball was being blown around as it came to you. We could use these methods to estimate how windy it was in the room or other things that might be impacting the ball that are not directly in the model equations. And in fact, the true power of these methods is in the last line. Because we have these samples of predictions of where the ball is going to be, these ensembles, we can do sample correlations of any function of the model variables with any function of the model variables. Okay, so that's extremely powerful. When I give this talk, I also stress it's extremely dangerous because one can madly correlate anything, and with small samples, one will get results that appear to indicate correlation and appear to give viable results, but they could just be noise. And so while these methods are very, very powerful, they must also be used in a responsible fashion. Before I go forward, are there any questions on some of these general things that you can do with these methods?
I have one, maybe a bit vague, but when you do this, the initial ensemble that you start with is, I assume, taken from a Gaussian distribution error model of your initial estimates. And then based on the probabilities you see from that first observation, you then generate a new set of ensembles, correct? That's the whole idea here?
That's essentially correct. And when I get to the Ensemble Kalman filter, that will be explicitly correct.
Okay, and then when you do that, to generate that second ensemble, I'm guessing you calculate a new error distribution that's on there, and you're assuming at every point, it seems to me, the easiest thing to do is you just take the mean and the standard deviation of, of that, or some probability weighted something mathematical transformation into a new error estimate on there, always assuming it's Gaussian. Is that a problem, or are there cases where that breaks down?
So you are correct. Yes, there are cases where it breaks down. I will not discuss them in this talk, but there are powerful non-Gaussian extensions to these methods, which are available in our software and elsewhere. As I describe the algorithm moving forward, it is going to be pretty much exactly as you described. And so there is this question of when you need those extensions, which I'll come back to at the end then. Okay, anything else? Okay, so quickly to tell you, I gave you this two-dimensional example, okay, of the ball being thrown through space. Turns out it's really a four-dimensional example because the velocity components are free state variables here. They've been hidden variables because they weren't observed and they didn't show up in the things, but we've already been working with a four-dimensional example here. And it turns out, I list examples for geoscientists here, but any prediction model can be viewed as simply the trajectory of a particle through a high dimensional space called a phase space, for those of you that are familiar with this. But basically, you can just think of having a set of axes where each axis represents the value of one of the state variables in your model. That means the evolution in time of the model is simply a particle moving through that high dimensional space. And it turns out that everything I've done is completely generalizable to any dimension without extension. Now, quickly, I'm a visual learner, so I like showing this with the picture, but I'm very quickly going to go through the mathematical derivation of this. There is one. And so x here is our state variables. It's a vector. It is a function of t. My forecast model is equation 1 here, so I can compute the time evolution of x as a deterministic part, which the ball had. I might also have some stochastic part in that evolution equation here. I have observations, which are called y. They're taken at times indexed by k. And I assume that there's some function h that maps from my model state variables at that time to what I think these instruments, there could be more than one, would observe. And there's also this noise, which was represented in the red circles. To make things easy for the derivation here, this is related to the last question. I'm going to assume that those noise characteristics are Gaussian with a zero mean here, but the methods can be extended to avoid those assumptions. I'm going to define now a capital Y. This is the set of all observations that were taken at times up to and including the current time. So if this were a weather model, I would have people who have been observing the atmosphere for many, many years. All those observations up to the ones that were taken this morning are available, and time tau is this morning. And with the probabilistic notation then, the probability of my state variables at time this morning, given all the observations up to and including this morning, so that's the latest observations, that's what I defined as an analysis. And forecasts are the probability of my state variables at some time greater than the time of my last observations. So it turns out then that there's two parts to this sequential process. One is making forecasts, and we understand that. The other one is probabilistically this. If I have an estimate of the observations up to and including the current time, I want to use Bayes rule, and this is a slightly unorthodox form of Bayes rule, but still found in the AP statistics curriculum, so it's fairly standard stuff. I'm interested in the probability of X given all the observations up to and including this current time. But really what I have is, I have this is the probability of X at the current time, given all the observations from the previous time. So this is my forecast for now, from the time I last had observations. This term here is the probability I would have observed what I did observe, given that forecast. This is called a likelihood formally. And there's this denominator here. Again, this is related to the previous question. To make the derivation straightforward for a short presentation here, I'm again going to assume that the noise is Gaussian and uncorrelated in time. Basically, this is just saying the observations taken this morning, the errors in those are not a function of the errors in yesterday morning's observations. It lets me simplify this likelihood term to look like this. And I'm going to, in the methods I have, be free to ignore the denominator, which is just a normalization. And so I end up mathematically with something that looks like this. My posterior, or analysis, my best estimate at a given time, t sub k, given all the observations up to and including that time, is the probability distribution of my forecast. That was the color-coded blue dots, multiplied times this likelihood, which was the red circles from the observation. This is in arbitrary dimensions at this point, though. So this could be a million dimensions if you have a forecast model that has lots of variables. So this is the math behind this stuff. Now, moving forward, we're going to have methods for solving this. I'm going to skip many of the methods that are around given the length of time here. Again, these are available on our webpage. If you're interested, I'm perfectly happy to talk to people after the talk at some time too. The particle filter was mentioned, and in fact, the method I was using where I did a huge sample of these trajectories and then evaluated their likelihood and gave them a relative likelihood that was the color, it's actually the most naive particle filter. The questioner pointed out that most particle filters do a resampling step, and basically that is when the observations from time half a second become available, unlikely estimates are eliminated and likely estimates are duplicated. It turns out that this makes this method much more efficient. However, it is still horribly inefficient for high dimensional problems. And so it cannot be used for the types of things that most of my users in geosciences use. The Kalman filter is another classical now method out of the early 1960s. If we go back to the equations we had, the Kalman filter makes a number of assumptions. This is related to the second question. It assumes that the model is linear, the deterministic part of the model. It assumes that if there is a stochastic part of the model, that it is Gaussian. It assumes that the state is Gaussian, and this was specifically, I think, what the questioner was about. It assumes that this mapping that gives you an estimate of the observations is linear, and it assumes, as we already did for this presentation, that the noise or uncertainty on the observations is Gaussian. If you do all that stuff, it turns out that long before Kalman, Gauss knew about this. He just didn't have big enough computers to make it worthwhile. If you're assuming that the prior in our equation is Gaussian, and you're assuming that the likelihood is Gaussian, okay, or normal, it turns out that in arbitrary dimensions that the product of a normal and a normal, a likelihood and a prior, is itself a normal, and it is trivial to write down what the covariance and mean of that posterior are. The covariance is the inverse sum of the inverse covariances of the likelihood and the prior, and the mean is the inverse uncertainty average of the prior estimate and the likelihood estimate. So this is what came from our forecasts. This is what came from our observations. If I go back and apply that directly to our Bayesian estimate here, as I said, I'm just going to have a Gaussian here and a Gaussian here. I'm going to illustrate the Kalman filter in the two-dimensional ball problem again. So if this is the X and Y position of the ball, I've now done a plot of a Gaussian, two-dimensional Gaussian distribution of our prior. So this is a statistical mean and two-dimensional covariance of all the blue dots from the previous time. The likelihood, this is basically just a contour plot of those things I showed as circles on the previous thing. So this is a two-dimensional Gaussian that talks about the error in the instrument. And the Kalman filter tells us how to take the product of these two things. That was the two equations I just showed. And the result is another Gaussian, which is located between our prior estimate, our forecast estimate, and our observation or likelihood estimate. And it turns out it's a little bit hard to tell from this illustration. It's a little bit closer to the estimate from our forecast model because this one, the green one, has less uncertainty. Its peak is higher and its width is less than the uncertainty that came from the observations. So this is the Kalman filter. Okay, it is widely used in a lot of low-order estimation problems, including things like trajectory estimates for a ball. But it has a number of computational cost challenges. And that is for big applications, like many of us are interested, where X, the state, is large. We would have to store the covariance matrix, so that is a size of X by size of X matrix. And we have to invert those matrices. That's a computational cost that is normally out of the question for these things, for big problems. So this leads us now to trying to find a computationally feasible way to approximate the Kalman filter. And we're going to do that by combining ideas from the particle filter with the math from the Kalman filter in the following way. Again, let this be the X and Y position of the ball at a particular time. And assume now that I have, in this case, 20 forecasts of where the ball is going to be at this time. The Ensemble Kalman filter gets rid of the use of the probability color from the particle filter by resampling at every time. And so each one of these forecasts is assumed to have the same relative likelihood. I know how to use the Kalman filter, and so I can just take the statistics, the mean and covariance from these 20 values here. Again, I have the red from my likelihood, and so I can use the standard Kalman filter to get a posterior estimate. And then I can somehow change my 20 prior estimates in green to 20 estimates in blue. And it turns out it's possible to do that in a way that these have exactly the sample mean and covariance of this posterior. So the ensembles allow me to approximate. In fact, it is more than an approximation. It is a way to compute the Kalman filter. That's a different way from inverting the matrices. Now, it turns out that this naive way I've illustrated is still impossibly expensive. And so the magic of Ensemble Kalman filters is in the following set of slides. The first thing is it is trivial to do a one-dimensional Ensemble Kalman filter. So let's say that we have, for this illustration, 5 forecasts of this morning's temperature. These are pretty good forecasts for the temperature here. They're probably pretty crummy forecasts for Mountain View, where I think it's about 60 this morning. And I don't know where the rest of you are. But let's assume anyway that this is our forecast for temperatures, 5 of them. That was not what I wanted to have happen. So let's see if we can get back to this for a minute. Sorry for the delay. Okay, we're going to fit the sample statistics here. So this curve is just has the mean of these 5 values and the standard deviation of these 5 values. Somebody takes a measurement this morning that says the temperature is 1 degree with an uncertainty of plus or minus 0.8 in this case. The Kalman filter tells me how to take the product of these, the green and the red curve. Okay, so there's the blue one. It's literally just the pointwise product of these two curves, it turns out. And then what I'm going to do is simply shift these green estimates, my prior estimates, so that they now have the same mean as the blue posterior. And then I'm going to linearly compact them so they have this around their mean, so they have the same standard deviation. So these 5 guys now have the same mean and standard deviation as the blue continuous curve. Okay, they're actually identical to the answer one would get from doing the continuous Kalman filter. Okay, so one dimension, big deal. So it turns out that without loss of generality, I can get the complete Ensemble Kalman filter for an unlimited number of state variables by just saying that I have a single observed variable and looking at its impact on a single unobserved variable. So example, maybe my observations at Mountain View, and I'm interested I have a model that also predicted the temperature this morning at San Francisco. I want to update that ensemble estimate at San Francisco. And so it turns out I can simplify everything to just looking at a sequence of bivariate problems with the observed mountain view temperature on one axis, the horizontal one here, the unobserved temperature at San Francisco on a vertical axis. I have the marginal distributions here, okay, for temperature at Mountain View and this weird vertical marginal for temperature at San Francisco. So the temperatures are roughly positively correlated. And it turns out if I do my one-dimensional Kalman filter for Mountain View, I get these 5 increments, 5 estimates in the change of the temperature at Mountain View that this observation gave me. It turns out that the Ensemble Kalman filter simply comes by regressing the increments at the observed place in Mountain View onto this bivariate distribution with San Francisco. So here were the 5 estimates of temperature at Mountain View and San Francisco. I slap a least squares fit through those. I then project the increments from Mountain View. Here's an example. This increment projects onto the slope of the red line like this. This one projects onto the red line like this. So I proceed to project all of the increments like that. And then I project those increments onto the San Francisco state variable. This is just a funky way, by the way, of illustrating what a regression does. So I project those increments on to the estimates at San Francisco, and I get 5 increments for the estimate at San Francisco. Not surprisingly in this case, since my observation said it was warmer than my forecast indicated at Mountain View, turns out that it's warmer. My estimate of San Francisco's temperature is warmer than my initial forecast too. So each one of these warmed up. And if I actually fit a prior and posterior to San Francisco, I find that my mean is warmer, and I've reduced the uncertainty. The height of the mean of the distribution, the probability distribution, is higher. So it turns out that without loss of generality, one can build ensemble Kalman filters for arbitrarily large systems by just doing these 2 steps. And so this is a cartoon illustration with just 3 ensemble members. That's normally too small. But I begin by taking my analysis, my best estimate at time t sub k. I make 3 forecasts to the time at which I next have observations, tk plus 1. I pick one of those observations at time tk plus 1. Maybe there is only one, but I take the first one in an arbitrary order, and I apply this H operator to convert my model state, which might be a big gridded value of temperatures. I convert it to just the temperature at Mountain View, for instance, say by interpolation. And so I get 3 values of forecast temperature at Mountain View. I have a measurement at Mountain View shown in red with uncertainty. I do the one-dimensional ensemble Kalman filter to get updated estimates of the temperature at Mountain View in blue and associated increments. And then I just regress those increments independently onto each one of the state variables of the model, whether there's 1, 3, or 3 billion. And the beauty of this is, as I said, those regressions can be done independently, which means they can also be done in parallel on large computers, and they're the majority of the computation. So we parallelize on large core sets for large problems at this stage in the algorithm.
So question.
Yes.
This is the most terrifying part of the algorithm. When
Okay.
you go deep into the internal state of a simulation and mess around with it.
I sure do.
Why does it work? Or why does it not make the whole thing crash in some weird ways?
So answer 1 is sometimes it does. And that would occur if the numerics of the model are sensitive to perturbations that go off of what we'll call the model's attractor. Now, because we're using statistics from prior model forecasts as part of our prior, these methods have a tendency to respect the restrictions that the model dynamics place on those priors. And so even in what we could call colloquially squirrely model applications, these methods tend to be fairly robust and to not put the model to places where it doesn't work. I will not kid you that there is often a struggle in new applications to understand exactly what the restrictions on the dynamics are. We've done that. We've worked with many, many dozens of large prediction models, including dozens in geosciences and dozens outside of geosciences. So there is lots of experience at dealing with these, and the problem is not as common as you might think.
Okay. If the values are discrete or categorical, how difficult is it to deal with those?
So I would like to take that question offline. The answer is that discrete or categorical is potentially problematic because the Kalman filter itself is really degenerate in that case. There are other methods, as I mentioned, that are extensions of these where the assumptions on the prior distributions are no longer Gaussian. And I have done 2 applications to discrete state variables successfully, but it is definitely an extension of the theory I'm talking about today.
Right. Okay.
So this theoretical part I presented to date, this is all theory-based. You can show that this, in fact, is the exact solution to the Kalman filter under certain conditions. And this is basically where this field was in 1996 when a guy named Geir Evensen in Norway developed the first Ensemble Kalman filters. So I'm going to show you now, those of us who do science of data assimilation like to work with low-order models that are certainly bigger than a 2-dimensional ball, but where we can still control the problem. We know the truth. And this is one of the most common examples. This model is called the Lorenz 96 model. Ed Lorenz, who is one of the people who did early work on chaos and geosciences, developed this model. He envisioned it as a model that is something like how weather evolves along a single latitude circle in the mid-latitude, so 40 degrees north. And in this case, there's 40 state variables. There's 40 locations along the latitude circle where we know the value of this. And then this model here allows you to make forecasts of how this state evolves. You can think of this as weather, but you can also think of each one of these 40 variables as being an economic indicator that's impacted by other economic indicators. Any type of prediction you could still think of like this. So an important point here is that this model is highly chaotic. So here I've plotted a single state that I've gotten by just making a very long forecast with the model from an arbitrary initial state. And what I'm going to do is I'm going to make tiny, tiny bit level perturbations to one of the state variables in that model. And then I'm going to start running 20 forecasts. Each one has been perturbed around that. And the red one will keep running too. I'm going to call the red the truth. And you can see that very quickly these little perturbations grow. And very quickly they become very large compared to the variability of the system. So that a forecast made even from an extremely accurate initial condition, like this one here, that forecast soon degrades in time. And so what we want to do now, just like the example I did with the ball, is we want to make predictions by using observations of this idealized weather around the latitude circle. So how I'm going to do that, simulate that, is I'm going to assume that there are a number of places around this latitude circle where somebody has built an observing station. And periodically that observing station can make an estimate of the true red value there. And so you can see here as an example, there's an observing station shown by the green asterisk at around 22. There's another one at around 23. Over here in the low number part of this thing, there's only a few observations. So there's one about 5, but there's none between 0 and 5. So densely observed, not densely observed, doesn't really matter. And I'm simulating instruments here. So the green asterisk is the value of the red curve, the truth there, plus a random draw from some distribution, a normal distribution that simulates the error of an instrument. And then I'm going to go ahead and use this procedure that I've outlined for you to assimilate these observations each time they're taken. I'm going to go back to the start here. I'm starting with this highly uncertain distribution I got from running these ensembles for a long time with no observations. And now I'll start moving forward, and every few times I make a forecast for a few time steps, and then I assimilate observations. I make a forecast, I assimilate observations. And as I said, this is where we were in the late 1990s. You don't have to go very far to see that this is not working. So the truth is in red, and I would like the blue ensemble to be a good forecast of what the red is doing. It's a crummy forecast because the blue tells me here where my cursor is, for instance, that the value is really quite a bit bigger than the red. And it also says we're very certain. All 20 estimates of that say, yeah, it's really 5. It's not -2. And so this is a very poor system. It's not working. And so there was a period of time where we were bogged down. If I go back to that idealization, there's all kinds of assumptions that we're violating here. One of those assumptions is that we're using, in this case, 20 ensemble members to estimate the covariance to do the regression when we use the observation to impact state variables. And it turns out that that is the first order error for many, many applications. And so we're going to have to find a way to solve that problem. And this is where we transfer from pure algorithm to that fuzzy ground between art form and algorithm. So we're going to put some heuristic modifications in here to make this thing work. And basically the problem is that if you're estimating correlations between an observation and a state variable so that we can do the regression of these state variable increments, the errors get progressively bigger as the correlation gets smaller. And so this is a plot that has true correlation on the horizontal axis and the expected error in an estimate taken from different ensemble sizes. So for the 20-member ensemble we're doing here, if you use it to estimate a correlation of 0.1, the expected error is twice as big as the actual correlation. And so what we're going to do is we're only going to try and use observations that are strongly correlated with state variables. So it turns out that for many applications, like this one, that the state variables and observations are strongly correlated when they're close to each other. So observations at Mountain View are strongly correlated with what's going on with temperature at San Francisco, but they're not correlated strongly at all with what's going on at the South Pole today. And so we're going to make a heuristic modification to the algorithm to restrict the range over which observations impact state variables. And that's what's shown in the top panel here. The bottom panel is what we showed before. And so if I go out a while, this is out at several hundred steps, you can see that the top panel is looking a lot better. It doesn't have these places where the forecast is completely wrong. And so localization is an important ad hoc extension to these algorithms. It's a little bit more than ad hoc. We know how to estimate this localization analytically from some extended theory, which I won't have time to go into today. But the bottom line is, for example, an observation here, it is not allowed to impact state variables out of this local space that's shown by the blue curve down here. Now, I've been yakking way too much today, which is interesting. Without having a live audience, I thought it'd be faster. It turns out that there is another heuristic extension to these methods that is also essential. And that is that normally we don't have perfect models of any system that we're interested in. There's all kinds of errors in the model. For instance, atmospheric models, they're not perfect. Our model of the ball wouldn't take into account things. And all of you, if you're thinking about prediction, you know your models have all kinds of problems. If we assume that the prior from the model is perfect, and the model really isn't perfect, we're being way too confident. We're giving much too much weight to the model, which is not as good as we think it is, compared to the observations. And so it turns out there's, in addition to localization, there's something called inflation, where we basically reduce our confidence in the model by just pushing the model priors out around their mean. So if this were my 5 forecasts for the temperature at Mountain View this morning, I say, well, really, the model's got some problems. I don't know exactly what there are, but I'm just going to say that the model's really too certain. So I'm going to increase the uncertainty in this prior around its mean, and then I'll go ahead and do the assimilation. And it turns out that despite the simplicity of this heuristic extension, it's incredibly powerful and has turned out to be able to deal with extreme model error. Again, I'm just showing you here. You can see cases without inflation. I've simulated model error here, and the bottom one shows you that sometimes things diverge again, so the estimate is terrible. But if you include these inflation techniques, which are, again, automatic, they can solve for these problems. So I'm going to go into a summary of what these methods can do now, and I'm going to start with a warning. Ensemble Kalman filters are provably optimal for linear models, Gaussian likelihood, and perfect models, which if you have those, you don't care about Ensemble Kalman filters. So for any real application, these things are an approximation. We're violating all these assumptions. The theory only tells us stuff about the mean and covariance, and so we can do some estimates of the errors there. But as I mentioned, you can do all kinds of other stuff with these ensembles besides just the means. As an example, you could say, well, what is the probability that it's going to be above 65 in Mountain View today? I have 80 forecasts, and 10 of them say that it's going to be above 60. I would like to say that 10 over 80, or 1/8 of the time, 1/8 probability it's going to be that warm. The bottom line is we don't really know a priori what statistics like those mean, and we know even less when there's all sorts of errors that we don't know about. So it is essential to calibrate and validate results that you use. And so that's just the warning. The conclusions are this. It's trivial to write a basic Ensemble Kalman filter. If you include extensions like inflation and localization, which have been studied for 2 decades now, it is possible to make these things work pretty much out of the box for a very large number of applications, and those applications can be huge. These algorithms can be made computationally efficient, both for scalar and large parallel computations. There are a whole bunch of hybrids with other types of methods can make these things more powerful. Quickly, in summary, what we do here is we produce a system called DART, the Data Assimilation Research Testbed, that provides tools to do this with arbitrary models and arbitrary observations. We support this tool. Everything is freely available. It is carefully software engineered compared to many, many other things that come out of geoscience institutions. It has a large user community, so about 1,500 registered users right now. It works out of the box with a lot of atmospheric prediction models, which a few of you may be interested in, but we've also had people apply this to social science, economics, other prediction problems, just the theory of prediction, so it can be used. And it is state of the art. So the state of the art in these things is operational numerical weather prediction, and we can do operational numerical weather prediction. Again, I can give you pointers to this system that was run in real time out of NCAR. It was the first system that produced mesoscale, so high resolution ensemble prediction over the continental United States. Again, I've yacked on far too long. I could show you many, many other applications. But I think the only way to make this valuable to you is if people have questions, I'm happy to hang on now and take them. I'll also give you contact information that comes to the entire team here. So dart@ucar.edu. This gives you links into our documentation and into a peer-reviewed paper that gives entries into. And sorry for taking so long, but I really appreciate those of you who hung in there live, those of you who may be watching later. And as I said, what's in this for me is we're looking for collaborations where we can help people learn how to use these tools. And so contact me if you have any interest at all. Thanks.
Well, thank you very much, Jeff.